Testing. Right. Right, we continue section 8.6 and 8.7. This is D. Right. Right. Good morning. I'm doing well. As mentioned yesterday, look like we're gonna have 19 days videos like this. So we're on the midway point right now. Alright. So we will not finish this problem. I'll just try to get going. For this problem, first thing, because I usually just move the dx to the back. And if it is in this form, we try to do partial fraction. And the partial fraction, remember, we only have linear factor or quadratic factor. This is a cube. So we have to be able to break this down further. Only linear or quadratic factors. Right. So different. This is the sum of two cubes. I'm going to use this. And if we have instead is a minus. The first will be the same. The second will be opposite. The last one is always a plus. So this is the difference or the sum of two cubes. When we go to chapter 10, we'll revisit this in much general case. Anyway, so we have 1 over x cubed plus 8 x cubed plus 8 we can write as x cubed plus 2 cubed. And that breaks down into x. So a plus b, x plus 2, a squared, x squared, minus ab plus b squared. So from here, and I'm not going to finish, but we do the partial fraction. It's not that difficult from here. It's just a little bit tedious. Just get the idea of how do we approach a problem like this. Right. Now, what I want to do instead is consider this one. Let's say this is the first example. So we have x cubed minus 2, and at the bottom we have x cubed plus 8. Right. Just make this up. Just try to get my point. This could be x cubed minus 2 or maybe something else. Right. So the difference between this one and this problem is this one, this is the fraction. The degree on top is less than the bottom, so that is actually a proper fraction. This one is called the improper partial fraction. Remember, whenever we do the partial fraction, degree on top is always less than degree at the bottom. This one is equal. Where we have degree of the top is greater than or equal to the degree of the bottom. In that case, we cannot just do partial fraction like we normally do. Right. In this case, what do we do? What we can do instead is the bottom is x cubed plus 8. Now actually we should divide in that case. For partial fraction where degree on top bigger than degree at the bottom, what we have to do is we have to divide first. So in this case, I divide the top by the bottom, but instead of dividing here, what we can do is this. Here we have x cubed plus a at the bottom. So what I do is I'm going to add 8 and minus 8. Right. So how did that help? So I'm going to group the x cubed plus 8 together. And minus 8 minus 2, that is the minus 10. And then we split this. X cubed plus 8 over x cubed plus 8, so we just have 1. So because of the 1 here, that make it improper. But of course, we're going to split 1 times dx. And this part, we're going to use partial fraction. Right. So, again, if we have degree on top is bigger than or greater than, bigger than or equal to the degree at the bottom, we have to split the improper part out because we can integrate that easily. And the remainder on the top, degree less than the bottom, this we can do partial fraction. The partial fraction here is where we have degree on top is less than degree on the bottom. That's the normal partial fraction. Right. Yeah. And of course, we continue from here. Partial fraction, like I said, a bit tedious, but not that difficult. So that's what I want to do instead of complete this problem. Right. So remember that. Make sure that the orange ink, you can read that well enough. Right, next. Right, so we'll try to evaluate this integral. Right, so how do we do this? Let me find a note for the previous section. Right. So usually we have 16, that is 4 square, 9, 3 square. So we have the sum of 2 square. So that is section 8.4 where we make the trig substitution. Oh, see. The 3 cases. When we see 2 square, usually that's where we make a trig substitution. So this one is not different. It's going to be trig substitution. But notice, this is a sum, so obviously we're going to use this one. Now, the difference here is we have a constant square. Yes, that's 4 square. But here we only have x squared instead of the 9. So we have to take care of the 9 first before we're going to use the trig substitution. But first, let's move the dx to the back. At 4 square. And the 9x, instead I will write as 3x square Alright, like this first. Now, first we just make a simple substitution or u substitution. We turn this 3x into a u. So we have a u square. That would be easy to do. So substitution, regular substitution. Right. Let u be 3x. So we'll have derivative is going to be 3 and move the dx over. We have du equal to 3 times dx, or we divide by 3. Du over 3 is equal to dx. Most of this problem in the section we have to make a preliminary substitution, so we bring that into the right form. Right, now we have 4 squared plus, instead of 3x, this is going to be u. And dx is du over 3. Right. So we make that substitution so that we have a variable square here. There's a 3. Take it outside. Stay at the bottom. Here we just have 4 squared plus u squared to 3 half power. Take out the 3, we only have du left. Right. Now when we have the sum of 2 squares here, that's when we make a trig substitution. So that will be a tangent, right? U equal to 4 tangent theta. Right. Take derivative. Derivative of tangent is secant square, and then we move the d theta over. And we have du. Right. Next. The 4 square plus u square. The reason we do the trig substitution, so we turn 2 terms into 1, and the square cancel the square root. That's the point here. So we go 4 square plus u square. U is 4 tangent. So that gives us 4 square plus 4 square tangent square, and factor out the 4 square. We have that, and 1 plus tangent square is secant square. Or we can say just 4 secant theta square. Right. Now we will put this back into this. And that integral will just continue. Right. 1 over 3 1 over. Right. The inside the bracket is 4 secant theta square and du is this. Right. So 1 over 3. Now, where we multiply this part, the square and the 2 cancel out. So multiply the power, 2 and 2 cancel. So we have just 4 secant cubed. Two and 2 cancel out. That cube. Right. Now, the cube will go to the 4 and the cube will go to the secant. So it will be 64 secant cube. Right. Now we can check all the constant outside. That's 4 on the top. Oh, sorry. I mean this constant. And the 64. One third. 4 on the top, 64 at the bottom. Right. Multiply. Inside we just have secant square over secant cube. Cancel out. 4 and 64 cancel. We just have 1 over 48. And we cancel 2 on the top. With 2 at the bottom, we have 1 left. So we just have 1 over secant theta d theta. Right. Now, this looks difficult, but actually very simple. Because 1 over secant is just cosine. And integral cosine is positive sign. Right, so it's not that bad. Now, all we need to do is rewrite this in terms of u, or at least, of course, later on we turn that into x. So rewrite this sine theta, and for that, I'll always go back to this, and we solve for theta. Or make a triangle. U equal to 4 tangent. So tangent is equal to u divided by 4. Right? And tangent is opposite over adjacent. So right triangle. Opposite over adjacent. And the hypotenuse therefore is going to be 4 square plus u square. And with that we go back to sine. Sine is opposite over hypotenuse. I'm just going to write 16 plus u square. Right, and we'll put back into our problem. U 16 plus u square, and then u finally is 3x. (16 plus 3x squared) plus c. (3 and 48 cancel, we have 16 left. So bottom line is we have 1 over 16 x over square root of 16. 3x squared would be 9x squared plus c. Right, so that's what we have. So this problem has almost a lot of integration technique. First, we just have a u substitution, regular substitution. And then we have a trig substitution. And then finally, just simplify. Right. That's what we have on that one. Next, next we have this one. I will change the plus to the minus. Just have some variety of problems. So I change this plus to a minus. Just want to have some variety in the problem. We have the plus already. Let's do a minus. So we look at this problem, kind of the same thing. A square root look like a square and a square. Right? So usually when that is the case, we make a substitution. So it will be the difference of two squares. In particular, it is one of those cases again. Right. So first, I will rewrite the problem as e to the 2x is going to be e to the x square. Because when we have power to another power, we multiply these powers, and that gives us 2x, like that. And the 4 is going to be 2 square. So we can take care of that suddenly. Right. So, however, we will turn this into a variable first. Turn this into u. First, so we will have different 2 square. Right, that is u. So the derivative is going to be the same thing. Move the dx over. And divide by the dx. I mean divide by e to the x. Right? And let's make that integral I. Right. E to the x here is going to be u. I should have written that u as well, but that's fine. Dx is du over e to the x. Right, it cancels anyway. So it's good. We only have u left. Right. So just make a simple substitution. Right. Now we're going to use the Trig substitution to turn these two terms into one, and that term is a square, and we take the square root, we cancel the square. So, and the substitution we use is variable square of variable square minus a constant square. That is case number 3, where we use secant. Right. So another Trig substitution equal to 2 secant theta. Right. And then we take derivative. Derivative secant is secant tangent. Move the d theta over. Right, so that is du. Next, we have to rewrite the two terms into one. Ideally, have the square root in have a square in it. We cancel with the square root. So u square minus 2 square. U square, u is 2 secant. square minus 2 square will give us 2 square secant square minus 2 square. Factor out the 2 square. We have secant square minus 1. Secant square minus 1 is tangent square. Right. So that is the reason we do the trig substitution. We turn two terms into one term. And not only that, it is a square. Which when we put it back under square root, the square and the square root cancel out. So that's the point of doing trig substitution. Right. Now put it back in here. We still have the integral I. 1 square root 2 tangent square tangent square. And the du is this. Right. Square cancel square root. To secant tangent right. Tangent cancel tangent. Actually the 2 cancel the 2 as well. So what's left is just secant. Right. And then integral of secant is ln secant plus tangent we have the secant. Now we just need to solve for the tangent. Right. From here u equal to 2 secant. So secant is u divided by 2. Right. Secant is 1 over cosine. So hypotenuse over adjacent. Instead of adjacent over hypotenuse. Make a triangle. Hypotenuse is u, adjacent is 2. So this will be u square minus 2 square. And what we need is tangent. Is opposite over adjacent. And then put it back in here. For some reason I just copied the problem again. Secant is u over 2. Secant is u over 2, and tangent is this. And finally, u is e to the x. So that's what we have. Right. So we make a substitution first. So we turn into something like this, and we can use Trig substitution. The square here, the u square minus 2. The u square minus 2 is the 2 tangent square, and we substitute it back in here. Square, cancel the square root. Yeah. So the square cancel the square root. Just convenient. So usually when we see the square root and then 2 square inside that, automatically it's a Trig substitution. Because when we do this, usually end up with the square and cancel with the square root. And on the previous problem, the 2 at the bottom is kind of like the square root. So we know that it's going to be Trig substitution because we have the square which cancel with the 2 at the bottom. So either square or anything resembling a square root, we need to do a Trig substitution. That will take care of this, because that gives us the square. We will take care of the square root. We cancel out. Right. The next problem is a little bit long, but I'm not going to finish the problem. Just make a simple substitution. Sorry, not that. G Right, so this problem could be long, but I just get the idea, and then we don't have to finish this problem. So for this, obviously, we have sine and then cosine. We can factor out the sine, but that's not the point. Now, if we rewrite like this, the sine x so what we do here is we do the substitution, regular u substitution, u equal to sine x, because derivative of sine gives us cosine. That would be easy. So u equal to sine x. We take derivative. derivative of sine is cosine. Move the dx over. And then divide by the cosine. Right? So pretty standard U substitution. Right. Substitute back in here. Here we have U square plus 2U. Yeah. So the difference in this problem is when we make the substitution, it's for 2 places, and then dx is du over cosine of x, and cosine of x cancel out. We have 1 over u square plus 2u du. Actually, after that will be easy. Partial fraction. So we use partial fraction after that. Right. We're not finished the problem. We're just gonna say it like that. Right. So this is that is the idea. Sometimes most of this problem we have to make the U substitution first to turn it into the nice form. And it could be partial fraction, it could be trig substitution, or it could be a lot of things. Like I said, the possibility for this is endless. But keep this in mind. We can only do a few type of integral. The integral that we won't be able to do is a lot more than the integral that we can do. So, and usually in engineering, for this kind of problem, when we see this, and we just look for the formula that have resemblance in that form, and then we just find the corresponding solution. Actually, the integration is a form of a calculation, and usually a calculation that should not be a problem. In real life, usually this kind of problem, I think calculator now can do this type problem. Right. Right. I'll talk about calculator. The next section, we really need to use it. So if you have it, make sure you have a calculator for the next section. If you don't have the calculator, remember at the beginning of the section, beginning of the class, I did send you a link where we can install a calculator on the computer, so we can use something similar to what I have there. Right, section 8.8, numerical integration. First, it's not part of the section, but just want to write. We used in physics a lot more. Than in math. Definition. Suppose C is the computed numerical solution. So I'm just going to write C is computed. And at the time when we do the computed, if there's any kind of numerical error or the calculator error, so that's just an estimate or approximation. Yeah, that's better. Yeah. All right. That is approximation. X is the exact solution. After that, we define absolute error. Is C minus X or X minus C, it doesn't matter. Because we have absolute values. Absolute values of a negative is equal to the absolute values of the opposite or the positive. And the relative error is going to be that absolute error divided by absolute values of X, assuming that X is not equal to 0. Right. So we have absolute error and relative error. I have some nice example here. So the ancient Greeks used 22/7 as an approximation of pi. Determine the absolute and the relative error. Right. By the way, I think in grade school, sometimes we use 22/7 as an approximation of pi. So, how bad is or how good is the approximation? Right. So first, absolute error. Just the absolute values. So we have the computed or the approximation, which is 22/7 minus the actual values of pi. So we just use the calculator here. What is 22 divided by 7? That's close to pi, actually very close to pi. So we're going to take 22 over 7 minus pi. We should do the absolute values, but it's not worth doing it. If we subtract and if we have no negative, just turn to positive at the end. It doesn't matter. We have absolute values. So the absolute error is 0.00126. And the relative error is 12. Is that divided by the actual values, absolute values of the exact values. Alright, so pretty much 0.00126 divided by pi. So on the calculator, go up, highlight that number, and then divide by pi. So it is 4.02 times 10 to the negative 4. So very small number. Right. So that is the Greeks. The next one I think is the Chinese approximation. We use 355 over 113. Of course, this is a lot more complicated one. If we have to do the calculation with this, of course, it's a lot more complicated than 22 over 7. But the advantage is this one is a lot closer to pi. So relative error is the approximation 55 minus pi divided by pi. So we have, again, I'm just going to drop the absolute values. 355 divided by 113. Oh, as you see. By the way, if you look into the my channel, the YouTube channel, and there's the banner on the top, there's a pi number on it. Anyway, so of course we're not even doing that. If you want to put everything on at once, hit alpha equal to, there's a fraction, and then alpha equal to another fraction, 355 over 113, subtract pi divided by pi. If it is negative, we just put the absolute values to it to turn to positive. So 8.49 has going up times 10 to negative 8. So that means this is extremely well approximation, like up to like 8 8 over 100 millions of algorithm. Right. So actually it's about 9:01. Let's take 5-minute break. We continue at 9:06. No, there's no reward approach, no reward application on this. It's just nice and all. Just appreciate the ancient people when there's no calculator and no thing, and they approach my pi up to this level of accuracy. So that is considered to be very well done. But all other than historical fact, I mean the calculator, when you hit pi, yeah, it gives you the more accurate answer than that. So not much real world application. It's just nice and all. However, what we learn in this section is going to be very important. There's a bunch of application for this. Right. Yeah, as always, if it is a little bit blurry, you should change back to 1080p. Right. What I'm going to do, make a little change of the overlay here. Move my picture here. Should make it smaller. I have to do this. Okay. Just for this section, because we use the calculator a lot, so I make sure that you actually can see the calculator as big as possible. Right, put my face there. That will do. Right. Yeah, that better. So I think you can see the calculator a little bit better. Right. We use calculator a lot in this section. So pretty much, maybe you appreciate the channel pace here, because we do a lot of integration in this chapter. Alright, now, we will have, in real life, there will be a lot of application involving this. So pretty much, the reason we have this is because sometimes it's difficult to evaluate the integral. Sometimes it's impossible to evaluate the integral. The only way to do it is approximation numerically, and this is exactly what we do here. Right. So we use the midpoint rule. Suppose f is define an integrable on an interval a to b. Now, integrable doesn't mean that we can integrate. By that I mean we might not have a function to do that. A prime example to that is nobody can integrate this. It has the solution, like from 0 to 5, for example. There is a solution, but we will not be able to write that in the exact form. There's always just an error. I mean, approximation. We will not have the exact solution for this problem. So the midpoint rule is, this is the approximation. The midpoint rule to approximate integral a to b using n subinterval. Is so we have the formula for this is the midpoint rule, characterized by m. We using n number of rectangles or number of subintervals equal to the first midpoint times dx, the second midpoint times dx on the way to the last midpoint times dx, or in terms of summation from 1 to n. We have the function. The midpoint would be characterized by sorry, there's a typo, should be a plus. Yeah, should be a plus in the formula. Right. Where, so that is the formula. Delta x is the width. We did this in calculus 1. B minus a over n. That's the width. And the midpoint so the midpoint, so in reality this is what we have. From A to B we divide this into equal segment. A is said to be A naught, I mean x naught. This will be x1, x2, and the last one B is xn. So when we take the midpoint, we're going to choose the midpoint. The point in the middle of each one is the average of these two values. So for example, the first midpoint m1 is equal to the average, and then so on. So in general, the midpoint mk is equal to xk plus x sub k plus 1 divided by 2. So the average of consecutive points, and of course xk equal to a plus delta x times k, and bottom line is when we put them together it's going to be that. Alright, Now, so that is the formula. And then there's a nice graph, which I will not graph it. So I just jump right into an example and see how it goes. Actually, I'm going to move the face cam next to the calculator. Doesn't have to be big. So this is count 1. So just get the idea is the interval will go from 2 to 4. So just draw from 2 to 4. Oh, by the way we evaluate this is the values of the function is going to be the height, the x is the width, the height times the width, give us a rectangle, and a rectangle, add all of them up, we have approximation of the area. Right, so from 2 to 4, and divide this into 4 sub-interval. So I will divide this into 4. So obviously this will be 3 in the middle, and between 2 and 3 is 2.5, and then 3.5. So there are 4 sub-interval. 1, 2, 3, and 4. Right. And this problem we use the midpoint. So the midpoint of this so the midpoint of 2 and 2.5 is 2.25, 2.75, 3.25, and 3.75. So those are the midpoints of each of the interval. Yeah, we did do this one even not even use the formula. And then so what we have is we have the midpoints. We're using this point to make the height. So pretty much we will write integral from 2 to 4 of x squared dx is approximately equal to just the height times the width. So the values of the function at the midpoint times the width, and the width of course is from 2 to 2.5, so the width is actually 0.5, or we say b minus a divided by n, 4 minus 2 divided by 2 divided by 4 is 0.5. So the width for one interval is 0.5. Uh, 2.75. .25. .75. Right, and we can just factor out the delta x. I mean the function is just square, but I'm just going to write that for a moment. And then delta x is 0.5. So I'll just go and write like that. Now the calculation using calculator. Right. So first we have the function, and then the values. I just want to do that in the most general case. So the function x squared, right? That's simple. Enter that into y1, and then quick. We're going to enter the midpoints in the bracket. So second bracket, 2.25, comma 2.75, comma 3.25, comma 3.75. Close the curly bracket and then store into L1. Hit the store key, second and 1. Right, so we put all those numbers onto this one. Let me write that, what we enter here. So first of all, y1 is equal to x squared, and then next we will have the list 2.25, .75, 3.25, and 4. Sorry. 3.75. Close curly bracket and then store into this one. Right. How do we actually type all of this? This is store, and we use the store key. And L1 is hit second button and then number 1. And the comma is easy. There's a comma button and the open parentheses. This is going to be second parentheses, give us the bracket. Right, so we have that. Now so we have the values. Now we will evaluate the values of the function. So to do that, we go to y1. There's a couple ways to do that. Either we hit variables, y variables, and y1, or just hit alpha, trace, bottom menu pop up, and choose y1. And to get y1, what's that? Alpha and trace. Yeah, that's y1. And we do y1 of those values. So y1 of this one, open parentheses, second one. Right. So we have all those values, which is good. Now, after that, we're going to add everything in the result. So we're going to add all of this up. So to get to the sum is second stat. Go to math. Second stat, and then go to math. Option number 5. Again, second stat, go to math, option number 5. Right, summation. And then the answer here is second, the negative sign. And hit enter. So pretty much we evaluate the function at those points, and now we add all of them up. And finally, just multiply by 0.5. When we do this, we have 37.25, and then we multiply by 0.5. And we have the answer is 18.625. Right, it might be a little bit complicated, especially if this is the first time you using the calculator. So that's why I go a little bit slow. And besides, there's a nice thing about a video, so you can always rewind to see how we did this. By the way, just how accurate is this approximation? Right, math number 9. We go from 2 to 4 of x squared dx. Yeah, so this is the actual values, and this is approximation. So it's kind of good approximation. Right, let's try another one. This. See, as sample 2. Approximate. So approximate that. The function is cosine plus 1. So the midpoint rule with n equal to 5 subinterval. Of course, there's a more generic way to do this, but just want to get the idea first, and then we'll go to generic formula later. Okay, I think I just keep this for now. Right. So in general, we have from 0 to pi over 2. Right, from 0 to pi over 2. If I can actually count. Right, first let's calculate the width. B minus A over N pi over 2 minus 0 divided by 5. So that gives us pi over 10. So the increment is pi over 10. So we have pi over 10. 2 pi over 10, we can reduce to pi over 5, 3 pi over 10, and then 4 pi over 10, 4 pi over 10, so be 2 pi over 4, 2 pi over 5, sorry. So we have from 0 to pi over 2 divided to 5 equals segment 1, 2, 3, 4, 5. And then we take the midpoint. Right, the midpoint between 0 and pi over 10, add them, divide by 2, give us pi over 20. And between this, we just add the midpoint, so 1 over 5 plus 1 over 10. I should do this. The midpoint. So the middle of 110 and 1/5 is 3 over 20. 3 pi over 20, and then between pi over 5 and 3 over 10, that is 5 pi over 20 pi over 4. And 7 pi over 20. There are more generic way to do this, but I just want to do this by hand first, so you get the feeling of what we have here. We have that, and then 2 pi over 5 and 1/2. Nine over 20. So those are the midpoints, right? So we just take the values of the midpoints, add all of them up, multiply by the width, right? So pi over 20 times the width, 3 pi over 20 times the width, 5 pi over 20 times the width, plus 7 pi over 20 times the width, 9 pi over 20 times the width, which will factor out the delta x. So simple enough. Yeah, that's a good thing. This is all online, so we pretty much can be anywhere right now, but mostly at home anyway. So we do that. So enter all those values onto the list. Let's see what we did. Right. First enter the function, enter the list, evaluate the list, add them up, and then multiply by delta x. Right. First, enter the function cosine of x plus 1. Right, we have the function. By the way, make sure that it is in radian. So it's good, radian, mode, radian. Alright, second, quick. Right, so we have the function. Now we enter the values. Open parentheses, pi over 20, 3 pi over 20, 5 pi over 20, which is pi over 4, and 7 pi over 20, and 9 pi over 20. And we have everything, right? And then store second. We store those points in list 1. If we want to, we can store it in list 2. So second, number 2. So we store everything to list 2, right? So Hope I entered that correctly. Right, it's good. So enter everything into list 2, not list 1. Next, evaluate the list. Alpha trace y1, which we could enter into y2. It doesn't matter. Right. Open parentheses, second L2. Right. And then we add all of this up. Second stat. Go to math, option number 5. Second negative sign. So when we do all of that, 8.196, and then delta x is pi over 10 times pi divided by 10. 2.575. Right. Now let's see if we calculate this directly. Integral 0.5 over 2. Cosine of x. Or we don't even need to enter the function. Remember, we already did. Right, so that look like a very good approximation. This is the exact values approximation. So good approximation. Alright, so like I said, this is a little more hands-on. What we could use is a little more generic. Right. Now we do this differently. On the test, I only ask you to do divide into 5 sub-intervals, something small enough it is manageable. But in real life, we might use 500, and we won't be able to calculate each one of them manually. So have to be a little more automatic. Right? So you can calculate the point manually, or we use the automatic formula, and so we don't have to do this. Right. So first, we have to know the function. So obviously, the function we know is cosine of x plus 1. And we store this into y1. Next, we calculate the width. Have to do this by hand. And we did this, we have pi over 10, right? We don't need to store that. Next, calculate the xk. Which is the sample point. So in this case, we have xk equal to a plus delta x times k. A is 0 delta x pi over 10 times k. Don't mind that, the answer must have k in it, so that is k. Then calculate the midpoint. So midpoint is equal to the average of consecutive points divided by 2. Right. So if xk is that, of course xk minus 1, by the way this is just pi over 10k. So x of k minus 1 is, just put k minus 1 in here, pi over 10 k minus 1. So pi over 10 times k plus pi over 10 k minus 1 divided by 2. And we're just going to leave it like this. And finally, the summation. K equal from 1 to 5. Oh, to n, sorry. And then we have the function at the midpoint times delta x. So k equal to 1 to 5, the function is still fine. The function of mk times delta x. Right, so remember we have this answer earlier. It was fine. Now, summation, math, summation. Right, instead of use k, why don't we just use x equal to 1 to 5. The values instead of f, that is the function y1, evaluate at the midpoint alpha equal to divide by 2, by the way. On the top we have another fraction of pi divided by 10 times k, which is x, plus another fraction pi divided by 10 times x minus 1 and then another fraction just times times pi with pi over 10. Right, we should get the same thing. Right, does that seem a lot? Yes, because in this case we have pi. That makes things a lot more complicated. So I will make one example with easier numbers, so we don't have to deal with all that. Let's make it simple. E to the x squared. Like I said, this one we won't be able to do it by hand. Using the midpoint rule. And when we have 100 intervals, that's kind of difficult to do that manually for all of them. So it has to be automatic. Right. So it's not that bad. Pretty much we just write out this part really. I mean, these 3 lines. Right, so I'm going to keep that there. Right. First, the function e to the x squared. That's easy. Next, the width. Delta x, b minus a over 2, b minus a over n, 5 minus 0 over 100, 5 over 100, 0.02. And then later on we're going to need to use that anyway. Sorry, maybe that's why I use a calculator. Sorry. Later we might store this into some values like alpha e, for example. We might even need to store that into e, so we don't have to work much. So e is delta x. Right. Next, we have the width. Now the sample point. Xk is a plus delta x times k. A is 0, delta x 0.05 k, which is just 0.05 k. So that is x sub k. Then x sub k minus 1. Just put k minus 1 here. Right. Then we can calculate the midpoint. the midpoint is the average of these two. We can leave it like that, or we actually can just multiply it out. I will do that. That give us 0.1k. Right. That gives us the midpoint, and finally the summation. Now we have 100 subinterval. So we go from 1 to 100. The function evaluate at the midpoint times delta x. So 1 to 100. The function evaluate at the midpoint delta x, the width. Right. So math summation, that I will use x, that go from 1 to 100. So 100 subinterval, they will enter the function. Nope. Second e to the x squared. Right? Right. Enter the function first. And then alpha trace y1. We will evaluate at this point a fraction 0.1 x. So instead of k, I use x. It's easier to type. Divide by 2. Let's close, not there. Right? Oh, too many parentheses. Come on. Right. That. And then times 0.05. Well, so 7.28 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's actually do this. Already enter the function. Right, so what we see here is this is not a very good approximation. Even when we use 100 subinterval, the answer is still a little off here. This is the approximation. This is the actual values. Right. The reason of that is because what we use is the rectangle to approximation, but the function can shoot off infinity. So we use the rectangle. It's not going to be a very good approximation because the function to increase so rapidly. Right. So bottom line is the formula can only put it back into only this form. So we need the width, need the midpoint. To get the midpoint, we need the sample points. When we have the sample point, find the midpoint, and just add the function at all those midpoint times delta x in the summation. So that's what we have. Right. Like I said, I'm just going to do this, but on the test, all we need to do is at this first example here, I just want to make sure that you know the rule and how to do this with like 4 or 5 subinterval, so be manageable when we can do this by hand. Because compared to the method that we study after this, so let's look at this, to the method that we study after this, probably the summation may not work very well. Anyway, we'll take a 5-minute break here, and then we'll continue at 10:10. Right. Now we continue. The Trapezoid Rule. Right. Suppose f is defined. I'm write the formula first, and then on this one we actually can prove this one. Yeah. Right. So the trapezoid rule using n rectangles. One half f of x naught and xn, that pretty much a and b. Just use a, be even better. Right? Either we use that or we factor out the 1/2 and we're using x naught, which is also a, 2 times the summation. Like I said, this one we will be able to prove this. Of course, I missed something from the beginning. Go back to that in a minute. Xn delta x divided by 2. Sorry. I forgot that this multiplied by delta x. Right. Of course, the width. So the whole thing have to multiply by delta x, where the width is the same as before, and the sample point the same as before, and it can be shown that trapezoid using 2 times n is equal to t if n plus m of n divided by 2. Right. What we're going to prove is this one. Proof. Then after this proof, then perhaps you'll get a better idea of what we're doing here. All right. So we go from A to B and doing for this much. In this case, 4 rectangles, 4 subinterval, and then we estimate the integral, which means the area under the curve. So say the function go like that. Now first, if we use the midpoint, do not write this down. I'm going to erase this in a minute. If we use the midpoint, we're going to take this midpoint and then we'll calculate the height based on the midpoint. And then the midpoint, calculate the height. Midpoint. And then the midpoint. So the area of all those rectangles add up together, give us the midpoint rule. Use the midpoint to find the height. Right. By the way, this is in calculus 1, so that's why I didn't prove that, which is very simple. Right. Now we use the trapezoid rule. The Simpson rule, when we learn later on, won't be able to prove as easily as this. Right. So the trapezoid. So what we form is we're going to take all the sample point here, and we form the trapezoid. So the height, and then the height. So that gives us the trapezoid. A trapezoid. Trapezoid. And there's a trapezoid. Right. So each one of them are trapezoid, and of course you see the trapezoid seems like a better approximation than the midpoint rule we have earlier. Right. Now, how do we calculate the area of a trapezoid? So all intention purpose, let A is x naught and B is x to the n. We have x1, x2, x3, and so on. Right. So how do we calculate the area of this trapezoid? So in general, for trapezoid, I could draw better. A, should not use A. base 1, base 2, and the height. Area is base 1 plus base 2 times the height divided by 2. I'm going to write like that. That area of a trapezoid. Now all we do is just turn this up, and base 1, base 2, then the height. So in this case, what we have is the area for that trapezoid is base 1 f of x naught plus f of x1 times the height, which is delta x. Divided by 2. That's the first trapezoid. The second one base 1, base 2 times the height divided by 2. And then the third one f of base 1 and base 2 times the height divided by 2. Right. Now let's just multiply now and see what happened. Yeah. And then when we add all of them up, we can factor out the delta x over 2. So what we have is fx naught plus fx1 for the first one. For the second one, fx1 plus fx2. For the third one, fx2 plus fx3, and then so on. Factor out delta x over 2. X, you see, there's one line on the left, one line on the right. On the line in the middle, there's overlapping. So you see two different colors of the line in the middle. In fact, we see the overlapping here, and then F3 with something else. So bottom line is, in the trapezoid rule, we have the initial point, and then 2 times every point in the middle. And then 1 point on the last. So that is the trapezoid rule. And of course, all of the one in the middle we can rewrite as a summation. Times 2. And that's the formula we have here. So notice that in the trapezoid, just the way we wrote, one line on the left, one right, one line on the right, everything in the middle are overlap. We count twice, right? 1, 2, 1, 2, 1, 2. So that's why we add 2 at the middle. Let's look at first example. Same thing. like I said, most of this problem we will do it by hand rather than using the summation formula like we had before, because I just want the concept. Remember, the idea here is 1 from the beginning, 1 at the end, everything in the middle. There are 2 of them, and then delta x divided by 2. Right. So now we just have the idea from 2 to 4. Two, 1, 2, 3, and 4. Right. From 2 to 4. First of all, always calculate the width. Keep doing that. So 0.5. Oops. So the width is 0.5, so we have 2 to 2.5, 3, and 3.5. So those are the points. And then the midpoint rule says 1 from the beginning, 1 at the end, everything in the middle, we have 2. So if we write the midpoint rule, it's going to be f of 2, 1 point on the left and 1 point on the right. Everything in the middle, there are 2 of them. Simple enough, right? 1 point on the left, 1 point on the right, everything in the middle, 2 of them. And then with that, multiply by delta x divided by 2. So that's all there is to it. That is the trapezoid rule using 4 subinterval. Simple enough, right? Right. Now, of course, we can just evaluate 1 by 1, but use calculator here. Right. Now, first, the function, of course, x squared. Right. So, x squared is a function. Now enter the points onto a list. 2, 2.5, 3, 3.5, and then 4. Right? And then we evaluate the values of the function. Alpha trace y1, evaluate at the list 1. Right, so we evaluate the function. The only problem here is we have 1, 2, 2, 2, and 1. The coefficient, that is. So in that case, what I do is when we do this, I will multiply that into another list of coefficient 1, 2, 2, 2, and then 1. Close that. No, I don't see there's anything wrong. Right. And try that again. List 1, 2, 2.5, 3, 3.5, and 4. 1, 2, 3, 4, 5. Right. Store that into list 1. Right. List 2, I will store the coefficient 1, 2, 2, 2, and 1. Store that into list 2. I see. The problem is that I know why. The list 2 we have the values earlier, we have to clear this out. So highlight the list 2, clear the list, clear, and enter. Let's do that again. Highlight the list, hit clear, and enter. Right. Alright, so we store that into list 1, which is good. Now we store this into list 2. What's wrong with this? Oh, second parentheses. Never mind. Right. Remember, second parentheses to get the bracket. I hope you see that well enough. That's the bracket. Right. So we store the numbers into list 1 and this into list 2, and then all we do is alpha trace y1, evaluate the function at the list 1, and then times list 2. When we do that, we have everything in the middle, and then we just do the summation. Second stat, go to math, option number 5, second answer. We have 75. I'm going to write out the step actually. Delta x 0.5 divided by 2. So 75 over 4 then. But in the spirit of approximation, let's just say 18.75. Right. Earlier we have 18.625. Right. Now, okay, let me write down the step. First, we store 2, 2.5, 3, 3.5, and 4 into list 1. List 2 will be the coefficient 1, 2, 2, 2, and 1. Store into list 2. And then of course y1 we already set is equal to x squared. What we do next is y1 of list 1 times list 2. And then finally we take the summation of that. And finally times. When we do that, we have 75. And take 75 times delta x divided by 2. And that's what we have. I'll have to clear a list, hit stat, and edit, hit enter. Very important that we have to highlight a list, highlight it, clear, hit the clear, and then enter. go here, highlight the list, hit clear, and then enter. That's how we clear a list. So pretty much this. Start to list 1, list 2, evaluate at list 1 times list 2, do the summation. So pretty much these steps. Right, we do the example of this. Right. On the test, I will ask you to do very simple like this, and we can use a calculator. I will not ask you to set up the summation like for 100 subintervals. That's a little bit much. Besides, when we go to the Simpson Rule in the next subsection, you get the idea of this. X e to the negative x dx. Find absolute errors. No essay. Midpoint Rule and Trapezoid Rule. Using, instead of 8 like in the prompt, let's just use 6. Six might not divide evenly, so let's use 5. Let's use 5 rectangles, 5 subinterval. Right, just get the idea, right? Right, so trapezoid and midpoint rule. Right. First, let's do the midpoint. From 0 to 1. As always calculate the width first. For both of those problems, we have the same width because of the same subinterval. 1 minus 0 divided by 5. That is 0.2. So 0.2 increment 0.4, 0.6, and 0.8. Right, 5 subinterval. Therefore, we have those points, the sample points. Right, midpoints. Midpoint 0.1, 0.3, 0.5, 0.7, and 0.9. So the midpoint rule, what we did was just add all of them up, multiply by delta x. So f of the midpoint, just use so add the values at the midpoints and then times delta x. Right, so how we clear this? Right, so enter the points. Let me just write out the step first. First enter the points. One, two, three, four, five. And then of course y1 is the function x e to negative x. That's the same for both midpoint and the trapezoid rule. And then we evaluate the function at least one, and then add all of them up. And then finally times delta x. Right, so just do those three steps. Right, open parentheses, second open parentheses, so we need the bracket 0.1 comma, just make sure, yeah, look clear enough on the screen. 0.3, 0.5, 0.7, 0.9, close the curly bracket, store into list 1. Right, evaluate that. Then we have the function. Now make sure you enter the function x times e to negative x. Right, and then we can alpha trace y1, evaluate at the list. Now add all of them up. Second step, go to math, option number 5, and either we hit answer or we just go up there, highlight, hit enter, so that copy and paste times delta x 0.2, and that's what we have. That is the midpoint rule. Right? And when we get used to it, it's not that bad. Now the trapezoid rule. Usually I draw a line so we know which point do we use. Trapezoid rule. Right. Draw a line again. Zero and 1. And the width is still 0.2. So the trapezoid rule, we're not using the midpoint, obviously. Trapezoid rule, we just use this sample point. So by the way, let's just write this as the midpoint rule using 5 interval. Now we use the trapezoid rule using 5 sub-interval. Right. Remember, one on the left, one on the right, everything in the middle will be twice of them. So f of 0, the one on the left, everything in the middle, there are 2 of them. So one on the left, one on the right, everything in the middle, there are 2 of them. And we just use all the points, all the sample points. And the difference here is we multiply by delta x, the width divided by 2. Right. Now, let's do this by calculator. So first we start those sample points. Onto this one, and then of course we evaluate that, but also the coefficient, where you start to list 2, 1 2 2 2 2 1 1 2 2 2 2 1. Start to list 2, and then evaluate the function at list 1 times list 2, and then do the summation. At the end, multiply by delta x divided by 2. Right, so it's simple enough. Right, the point. Open bracket 0, 0.2, 0.4. Just make sure that it look okay on the screen. 0.6, 0.8, comma 1. Close the curly bracket and store into list 1. Right? Actually, we don't even need to clear the list. As soon as we store it, it will replace. I think it's better. I just make sure that if you want to make sure it's right, hit the stat and edit. Alright, those are correct. We can enter the numbers in here if we want to. 1, 2, 2, 2, 2, and 1. So this exactly is the same thing as we enter that into the list. We can just again, let's quick here, hit the stat button, just the stat, no second, just stat, hit enter, and then we can enter the numbers here on the list, list 1, list 2. Not the same thing as store into a list like this. Right. And then evaluate the function. Did we enter the function? Oh, already did. Right. Alpha trace y1, and we're going to do all of the list 1 times list 2. Right, we have that. Now we just need to add all of this up. Second stat, go to math, option number 5, and either we do second answer, we have that, or I just go up there, highlight it, hit enter, copy and paste, and at the end multiply by delta x 0.2 divide by 2, and we have 0.2609. So it's not that bad, right? You see, it's always raw line, so we know what pointer we use. The coefficient for the trapezoid rule is 1 on the left, 1 on the right, everything in the middle. The coefficient, that is 2 times everything in the middle, 1 on it, and right. So we have that, and then the absolute errors, we haven't done that. So pretty much we take the exact values of this, subtract the midpoint rule using 5 interval, and then the trapezoid rule using 5 intervals. Right, so 1 minus 2 times e to negative 1, subtract, right, m5, where's m5? I just go up. Oh, that is m5. Highlight it, copy and paste. And doesn't matter, we have absolute values, so we just write the positive answer. Right, and then we take that number, subtract T5. T5 is this. Highlight, copy and paste, and we have this. Sorry. Nothing happened, right? Okay. I forgot the 2 here. Right. Right. Now, actually, when we look at this, we see that the midpoint rule is more accurate than the trapezoid rule. Furthermore, the error look like this one is twice as the other. And why is that? Because later on at the end of the section, we learn about the error, and the error in the trapezoid is going to be twice as the error in the midpoint rule. But I said it doesn't really matter. Right, so just draw a line and then choose what pointer we use, evaluate the function, add them up, multiply by the width. Trapezoid, kind of the same thing, but we have to multiply by the coefficients and then multiply by delta x over 2. The Simpson rule we have is still the same thing, but instead of the coefficient of 1, 2, 2, 2, 2, 2, 2, 2, 1, the coefficient for trapezoid is 1, 4, 2, 4, 2, 4, 2, 4, 2, and then 4, 1. So if we use the trapezoid rule, the coefficient will be 1, 4, 2, then 4, 2, and then 4, 1. So instead of using all the 2's in the middle, we use 4, 2, 4, 2, 4, 2 alternating. So that the trapezoid, the Simpson rule. So pretty much similar to what we have for these two rules. But I think I'll stop here and then save that for tomorrow. For Friday. Right. When we have this, when we finish this, we go to next section. So we're back to the integral. This section kind of on the approximation, and then we'll go back to that, and then we'll go to chapter 10. The next test, I think, should be ready by Wednesday. So I post the test by next Wednesday. The review should be before that too. So the next test will be 8.4 to 10.4. Right, I'll make an announcement for that, more details on Friday. But other than that, I'm going to end the stream here. Do you have any question before I end the stream? If you have no question, I'm going to end the stream here.